Section 6.1 of your textbook introduces the topic of rational expressions. A rational expression is any expression that can be written as a quotient of two polynomials. Three examples are shown on the slide. Our first rational expression, 5 over n, has a constant in the numerator and a monomial n in the denominator. The second example has a monomial in the numerator and a binomial x plus 6 in the denominator. And our third example has a trinomial in the numerator and a binomial in the denominator. Now remember that a rational number is any number that can be written as a quotient of two integers. Notice the similarity between that definition and the definition of a rational expression. The similarity is important. It points us to the fact that the processes used to perform operations on rational expressions are actually the same as those used to perform operations on rational numbers. Now, since rational expressions generally contain variables, sometimes we'll see that replacing a variable in a rational expression with a certain number would make the denominator have a value of 0. This creates an expression which is undefined because division by 0 is undefined in math. In such cases, we say there are restrictions on the expression, values for which the variable is not allowed to represent. Let's look at some examples. We're going to list all numbers for which each rational expression is undefined. Another way of saying this is we want to identify the restrictions on each expression. Our first one is 1 over the quantity x plus 2. In order for this expression to be undefined, we would need the denominator, x plus 2, to have a value of 0. And we can see that in order for that to happen, x itself would have to equal negative 2. So we say that negative 2 is the value that makes this expression undefined. Another way of saying that is there's a restriction on this expression. X cannot equal negative 2. Let's look at a second example. In this case, we have a binomial over a trinomial. And in order for that expression to be undefined, the trinomial, x squared plus 3x minus 4, would have to equal 0. Notice that here we have a quadratic equation, so we can solve it by factoring the left-hand side. And then using the zero product property to obtain two solutions, either x equals negative 4 or x equals 1. So in this case, there are actually two values which would make the rational expression undefined. Both negative 4 and 1 would result in a denominator of 0. And so we would say that x cannot equal either of those two numbers. Finally, look at the third rational expression. If we want this expression to be undefined, the denominator would need to be 0. It's a quadratic equation, so if we factor the left-hand side and use the zero product property, once again we see two solutions. In this case, 0 and 7. So both of those values would make the denominator equal to 0. Both of them would make the original expression undefined. And so both of them are restrictions on our variable. To simplify a rational expression, we use a process that is identical to the process used in simplifying rational numbers or numerical fractions. We remove common factors from both the numerator and the denominator. Let's look at some examples. Our first rational expression is 3n squared over 12n. In order to simplify this expression, it's helpful to write it in factored form. We can write 3n squared as 3 times n, and the denominator, noting that we saw that factor of 3 in the numerator, we want to factor 12 as 3 times 4, and then we also have times n. Comparing our factors, we see that there's a common factor of 3 in the numerator and denominator, so we can remove those, since 3 over 3 has a value of 1. And there's also a common factor of n in both the numerator and denominator, so we can remove those, since n over n also has a value of 1. This results in a simplified rational expression of n over 4. Let's move to example 2. In this case, we have a binomial in the numerator and the denominator. We cannot simplify this expression until we have written it in factored form. So let's use the distributive property to factor out the GCF of both terms in the numerator. So we have 6n times the quantity n plus 3. And in the denominator, again using the distributive property, we can see that we have 4n times the quantity n plus 2. Now looking for common factors, we see a 6 and a 4 which have a common factor of 2. So we can write that as 3 over 2. And we also see a common factor of n in both the numerator and denominator. And then looking at our binomials, n plus 3 and n plus 2 are different binomial factors. Even though the first term of the binomials is the same, since the second term is different, we cannot simplify those binomials. So our simplified rational expression would be 3 times the quantity n plus 3 over 2 times the quantity n plus 2. Let's move on to example number 3. In this case, we have a trinomial in our numerator and a binomial in the denominator. Once again, before we can simplify, we need to factor both the numerator and denominator. In this case, x squared plus 10x plus 9 factors as the quantity x plus 9 times the quantity x plus 1. And our denominator, x squared minus 1, is a difference of squares, so that factors as the quantity x plus 1 times the quantity x minus 1. Note that in this case, we do see a common binomial factor. X plus 1 appears in both the numerator and denominator, so we can remove it and write our simplified rational expression as the quantity x plus 9 over the quantity x minus 1. Let's look at one final example. In this case, we have a trinomial in both the numerator and denominator of our fourth rational expression. We need to factor both the numerator and denominator. The numerator factors as the quantity 5x minus 2 times the quantity x minus 1. The denominator factors as the quantity x plus 4 times the quantity x minus 1. And again, we see a common binomial factor, in this case x minus 1 over x minus 1. Removing that factor, we have a simplified rational expression, 5x minus 2 over x plus 4.